today I'm going to talk about multimodal self-supervised learning from videos. But just to start with, I would like to give a bit of motivation about self-supervised learning. So I guess, as many of us know, supervised learning has been at the origin of impressive successes over the past few years, and especially in computer vision, such as applications like pose estimation or image segmentation. And we also know that the success of deep learning relied a lot on labeled data. But I think there are basically two issues with supervised learning. So the first one is, of course, the time and money that is needed to get those labels. But the second one is also the fact that labeling is hard to define in the first place. So for example, if I were to give you this image on the right, and I would ask you to label the man in the image. You could, for example, decide to label it as follows, or you could decide to include the at in the definition of the man. And this is actually what was done for this image in the COCO dataset. So there is this issue of agreeing on what is the right ground truth. And there is also an issue of granularity. For example, in this image, what should we annotate? So should we annotate every instance of the sheep, the dog, and where should we stop? Should we annotate every blade of the grass? So again, this kind of supervised learning kind of has a limit because we cannot decide to annotate the whole world. So of course, I guess some of you, and I think, yeah, sorry, this problem I think is even worse when we move to videos because there are even more possibilities due to the temporal aspect of videos. For example, how to agree on localizing actions, how to come up with a predefined list of actions that this guy can do with the tool he has. So yeah, this problem is even more pronounced on videos, and we need to kind of address this issue. And I guess many of you know, because some of your work in your lab are about self-supervised learning. And so there has been this approach to kind of avoid labeling data, but try to directly learn representations from data itself. And one very good technique that has come up over the last years is what is called self-supervised learning, where the basic idea is to design a pretext task from your data that do not require any manual annotation, but from which you're going to learn something about the data. And here I'm citing this paper from ICCV 15, which was given an image trying to predict the relative position of two patches extracted from the image. And basically by doing so, you will, for example, try to learn where the face of the cat is relatively to the ear. And by learning this, you will be able to learn a good representation about the image. And again, you don't need any manual annotation for doing so. You just need raw images. And maybe more related to the topic of the talk today, another way to kind of design those pretext tasks is to use multimodal data, for example, coming from video, where, for example, you can take a video and its audio signal and try to predict whether or not the audio and the video are in sync together, whether or not they are a positive instance, meaning the audio is from the video or not. And by doing so, again, you're going to learn very good representation about the video and the audio, because you are going, for example, to try to correlate the sound of the violin with the visual of the violin itself. So that was a paper from ICCV 17. In this talk, I will focus on one particular type of modality, which are narrations. So narrations from videos can be obtained automatically from automatic speech recognition. So we take the raw speech signal, but we extract what the people are saying in form of text. And yeah, I'm going to show that we can actually use this kind of data to supervise our algorithms for free. And one particular type of data I'm going to use are instructional narrated videos. And I'm going just to illustrate what are those with a short video. So basically, those videos are for example, you don't know how to change a car tire, and you can go on the web and type, how can I change a car tire? And you will find people explaining like step by step how to achieve that task by using language narration, as well as demonstrating visually how to do the task. And as you can imagine, this is a rich source of data for supervision. And the nice thing about this is that you can get that at scale. So there are lots of videos of people changing a car tire, but it's not only about changing a car tire, it concerns lots and lots of other tasks, ranging from like gardening to health or cooking. And like motivated by this, we collected back when I was still at INRIA before DeepMind, the How-to-100M dataset. That is kind of one of the largest dataset available right now for video and narrations. And it was obtained from querying YouTube with a list of human tasks coming from a website called WikiHow. And so it contains roughly 20,000 human tasks. And in total, it has 1 million videos that we've cut into 100 million clips that comes with this kind of narrations obtained from the automatic speech recognition. So of course, it's kind of noisy because the narration not always corresponds to the video, but we have it at a very large scale. And so we believed that we could learn very good representations from this data. And this is one of the things that I will talk about today, how to basically learn from this data. And so that will be the overview of the talk. So I will present two of our recent papers. The first one was presented last year at CVPR 20, and is basically just trying to learn visual representations from those kind of narrated videos. Then in the second part of the talk, I will discuss how we can generalize what we've done in the first part of the talk to more modalities, and especially trying to use and leverage the audio modality and not only using the language from the ASR. So yeah, let's dive in. Let's start with the first work that is entitled End-to-End Learning of Visual Representations from Uncurated Instructional Videos. And the main question we are going to ask in this talk, and I'm hoping to give you a good answer, is how can we learn good visual representations using narrated videos without any source of extra supervision? And basically the approach is as follows. So our video representation learning tasks consist of sampling a video clip of a few seconds with its aligned narration. So as in this example. We will then embed both video and the narration into a joint text-video embedding space. And finally, we use a video and text contrastive loss to match the video embedding with its narration embedding. So you might be familiar with contrastive loss in the case of learning representation from images, where you create two views, one from by augmenting the data, and use a contrastive loss to have like positive image being close and negative pairs being far. But here we use it, the same principle, but where the two views comes from the two different modalities. But yeah, as simple as it may seem, there is a challenge with this data, and that I'm going to just show you a video to illustrate this.
For today, Mediterranean style, keep it simple. You just want to add some fresh herbs, maybe some oregano. You can add cilantro, basil, and give it a couple more tosses.
So this is a typical example of a video we have in our data set. And basically, if we were to just sample a video clip with its aligned narration, we should have to match these two inputs here. So fresh herbs, maybe some oregano, but unfortunately, we do not see those words happening in the video. So in this work, we address this issue by instead considering a set of positive candidate narrations coming from neighboring timeframes in the video. And as you can see in this example, if you do that, you have more chance to have some narration that will match what is happening in the video. So So now, how do we adapt the first principle I showed you to this kind of case where we have not only a single positive candidate, but we have multiple positive candidates with some potentially being wrong? So what we do is we do the same as before. We take the video clip and the different narrations. We embed them into the space. And now we will propose a multiple instance learning contrastive loss, which is going to only match, hopefully, the video with the most relevant narrations from the candidates. So in that case, for example, there are like 2 that are correlated and another one that is not. But we want to we don't want to penalize the model for not aligning all the narrations at once. And so how exactly are we going to do that? So this is the loss we introduced, which we've called multiple instance learning noise contrastive estimation, or MIL-NC. And that is going to have a flavor of noise contrastive estimation, but with a flavor of multiple instance learning that enables to learn from a bag of positive where not all instances in this bag are necessarily correct. So again, we will have a video network F that will take the clip and the video clip and extract the representation from it. Basically, just think about a vector in a space. And we will have a similar network for the text that will extract a representation for the text. And then based on those, we can extract, we can obtain a similarity between the clip and the narration by just taking a dot product and taking an exponential of that. So then what we can do is, given the bag of positives, so like those different positive candidates that we have in our bag, we can sum their score to obtain a global score for the video and the bag of clips. Next, what we can do is apply the contrastive idea, where we have the score for the positive that we are going to contrast with some negatives that we are going to sample from our data set. And just to better illustrate this, in the previous example that I showed, the positive bag will be basically the video clip with the different narrations that we have. So that will be like 3, our bag is of size 3. We have the clip and the different narration. And for the negatives, what we do is basically construct negative pairs by taking either video clip and narrations coming from other video in the batch, or taking a video clip from another video in the batch and a narration coming from the current video. So we are building those negative pairs to be able to contrast with the positive. So I hope this is kind of clear, but feel free to interrupt if you have a question at this stage.
Can I ask a question?
Yeah, of course, yeah.
So here for the clip that you mentioned, it's not just a frame, right? So you are...
Yeah. Actually, I'm just going to show how do we model like what our models looks like, and I will explain that we have like more than a frame. We actually have like 3 seconds of video.
Okay, then I'll wait for your explanation. Thanks.
Yeah. So yeah, now I'm just going to explain what are the text model and the video model we use. So for the text model, we use a kind of a simple text model where we start from a sentence that we separate into words and obtain vector for all of those words, for example, using word2vec. And then we simply use a kind of 2-layer network that that process those words first independently, then do a max pooling to obtain a single vector. And then with a linear projection, we project this, this representation into our joint embedding space. So for the video, so this is going to answer your question. We sample 32 frames of video at 10 FPS, which is roughly 3.2 seconds. I mean, which is exactly 3.2 seconds. And we use a 3D CNN backbone, but you could use any video backbone available to extract a vector that we also then linearly project to this joint embedding space. So what do we mean by joint embedding space? It's just that the dimension of the text embedding and the video embedding is the same, so that we can compute dot product between them. So I hope that answers your question.
Yes, thanks.
So then, yeah, what we do is like we train those two models end-to-end on the auto-1M data that I talked about before. And in particular, it's important that we really start from scratch. So we don't use a model that was pre-trained on some supervised data like kinetics or ImageNet. We really want to show that we can learn good representations solely using this narrated material. So we train those models from scratch on the auto-1M data. And now the question is like, once we've done this, how are we going to evaluate the visual representations and kind of making sure that what we have learned makes sense and can be useful for different applications? So I guess one standard thing in the domain to do that is to use downstream tasks, where we are going to either learn just a small layer of adaptation for a given downstream task, or fine-tune the network to a given task, or even, as I will show later, being able to do directly zero-shot on some tasks. So for that, we consider various tasks. So in terms of just evaluating just the video representation alone. So the first one we consider is action recognition on two benchmarks that are kind of standard in the literature of action recognition, which are HMDV 51 and UCF 101. So there are both small data sets of, so for HMDV, it's 51 human action classes, and UCF 101 contains 101 action classes. So we also look at action localization, where the goal is not only to give a label to a video, but also localize where the action is happening in the video. And we do that on 3 benchmarks. So the coin, the YouTube item segments, and the cross-task dataset. And as I will explain later, we also look at evaluating the text to video retrieval. So not only using the video backbone that we take in as isolation, but also using the text branch that we've learned to be able to do text to video retrieval. And we do that on 2 benchmarks. So MSRVTT, which is kind of generic videos annotated with language. And uCook2, which is more tailored towards cooking videos, which is a bit more in domain with the auto-1M data that has lots of cooking videos. So I'll just show the results that we had at the time. So since then, like, people have improved, and we will see in the second part of the talk that we can get better results than this. But basically at the time, on UCF 101 and HMDV 51, we obtained like the state-of-the-art results compared to previous self-supervised video representations. And that was quite interesting for us, because previous approaches were training the representations on videos that were already kind of tailored towards action recognition, whereas like our data set was not specifically designed to recognize like human actions that are maybe present in HMDB or UCF. So like that was a really good positive result. But maybe even more interestingly, when we were only fine-tuning the last linear layer or in the zero-shot setup, we were able to even outperform fully supervised representations trained on ImageNet or kinetics on different benchmarks, such as MSRVTT, the cross-task dataset, the coin dataset, and also the YouTube item segment. So this was a really good proof for us that, like, you know, this self-supervised approach is valid and can actually replace trying to manually annotate the data. And yeah, so this is basically like really strengthen our hypothesis that large-scale self-supervised training can be a better option than training on smaller scale supervised data sets. So now, as I said before, I said that, so up until now, I was just showing the results with only evaluating the video representation alone. But the nice thing that we have as a byproduct of our training is this joint embedding space with the text and the video. And so we can try to evaluate how good is this joint text video representation.
Can I ask a question before
you
move on? So about the results in the previous section, did you just use the 3.2 seconds of each of the video for the evaluation, or you basically passed a couple of, let's say, seconds and then concatenating them to have the final prediction?
Yeah, so that's a really good question. So in general, it depends a bit on the evaluation. But for example, to give you a concrete example, on the HMDB and UCF, the video are a bit longer than 3.2 seconds. So what we typically do, for example, in the linear evaluation, we will extract multiple clips from the training video and learn a linear layer on top. And during evaluation time, what we usually do is we will uniformly sample, for example, 8 or 10 clips from the video of size 3.2 seconds to not introduce any discrepancy between the training and the testing. And we average the results over those 10 clips.
Okay, so you do average basically, not concatenation. Okay.
Yes, we do average. I think you can also do concatenation and kind of run the model in a fully convolutional way. Mm-hmm. But I think nowadays it's more standard to just extract subclips of the same size of what was used during training. And okay. Then average you average the prediction after the softmax.
Okay, thanks.
Yeah, thanks. I'm happy to give more details about this offline as well, if you need.
That's fine for now, thank you.
So yeah, coming back to trying to evaluate the joint text video representation. So one thing we can do is to do text-to-video retrieval. So let me explain how this works. So yeah, So we start with a collection of clips. What we can do is embed them into the space. So we can do that offline. And then now, given a query, we can embed this query into the embedding space and retrieve the video that has the closest embedding with respect to this query. And now what we can do is take a video dataset that has both video and text annotation, for example, the UCook2 dataset, and we can evaluate with a metric called recall at 10, which will basically count for every query in the dataset, how many times we retrieve the correct video in the top 10. And so this dataset, I think, has around like 3,000 video. So the kind of the random performance will be really bad since it's roughly like 10 over 3,000. And here we observe an interesting behavior that I'm going to explain. So in one of our previous work, what we were doing is that we were basically taking pre-trained representations from ImageNet and Kinetics, and we were freezing the visual representation and just learning the correspondence between the text and the video by just fine-tuning a few layers to compare the text and the video. And these were the results we were obtaining at the time by doing kind of a zero-shot text-to-video retrieval on this UCook2 dataset. So around like 25 recall at 10. Then what we could do back then is also fine-tune on the UCook2 data itself to further improve those results. But what we had in this work is that without any label used for pre-training, so we were not using any more ImageNet or Kinetics, and we were not fine-tuning the representation on UCook2, we were able to improve significantly the retrieval performance. So this, again, like comforts a lot our hypothesis that by really training end-to-end on a very large data set that is uncurated, that contains those narrations, we can improve a lot upon like supervised pre-training for this kind of task. Yeah. So I don't know if there are some questions about the text video evaluation. Otherwise, I'll conclude the first part of the talk.
Do we have any questions? I think you're gonna finish the CVPR and then jump to the NIPS, right?
Yeah. So I'm just going to give a few like takeaways that I think are interesting, and then we can take some question there, and then I'll move on to the second part.
I have a question about the fine tuning for downstream task for the action recognition. Can you just explain? So use the basically you try different ratio of the labels for the fine tuning.
So we haven't really explored that, like what is done, I guess, in some ImageNet paper where you vary the number of labels.
Right.
What we did, like there are basically two regimes. So one is you only learn a linear layer on top of the frozen representation, or you fine-tune the whole network. But the difference with kind of the ImageNet setup, where you kind of want to see with few labels how it will behave, is not as relevant here for HMDB or UCF because they don't have lots of labels already. So it's already this kind of small scale kind of fine-tuning regime. So yeah, I think I forget. I think HMDB is maybe 3,000 video only. So basically, yeah, it's already kind of this small scale transfer regime.
Yeah, I got your point. Yeah.
Cool. Yeah, so I'll just highlight some key takeaways. So first, we've introduced this mill and C loss, which I think is a really good way to learn representations in an end-to-end fashion when having uncertainty on your set of positive labels. And this was not really like explored or done before in the case of self-supervised learning. And I mean, in the paper, we compared, of course, with different alternatives. For example, taking the easiest positive by taking the max in the loss. But we observed that this formulation worked the best. So in terms of video models, another observation that we had is that like the performance was increasing a lot with the visual model capacity. And this is something that we further observe in our following work. And I think this kind of behavior might be even more pronounced for such large scale regime, like when we have like 100 million clips, compared to like smaller supervised setting like kinetics, which has only, I mean, which is big already, but like less than 1 million training clips. Second, I think one interesting fact that we observed, I mean, you may be aware of all the advances in language modeling, but in this work, we observed that the simplest model worked the best for us. And this is something we are still kind of investigating and exploring to understand better. But in our case, like for example, using transformers on the language side was not really helping. So we have a few hypotheses about this, but we want to explore this further. Also, one thing I want to mention is about the batch size. So you may know that like in this self-supervised regime, and especially the contrastive learning, like the number of negatives grows with your batch size because you will use all the other instances in the batch to create your negatives. And what we observe is that like when using very large batch size, we got like really great gains and very good performance gains. And again, this thing has two effects, increasing the batch size. So first, like we get more negatives as positives, and we observe in our ablation that this is quite important. But also it enables to better optimize the objective since we do more epochs under the same time budget. If you have like the infrastructure that scales linearly, which is kind of our case at DeepMind, but this is something that is kind of complicated or more hard to get in a more academic setting. And so I believe this kind of remains a challenge in the domain, and we should try to find alternatives that do not specifically require such large batch sizes. And yes, so we've basically, we have a website where you can actually try and play yourself with this demo of zero-shot text-to-video retrieval on the UCooCute dataset. So you can like type any query and see almost in real time the results that are retrieved by our model. And also on this website, we've made our text video model publicly available, both in TensorFlow and in PyTorch. Which I think also is really important for the community, especially since not everyone has access to the same training infrastructure. So yeah, with that kind of concludes the first part of my talk. So if there is any question about this, I can take that now. Otherwise, I'll move on to the next part.
Is there any question? So I have a question about the batch size, because you mentioned you need very large batch size. I mean, is there any like a alternative based on dictionary, like a MoCo approach, which can be used as replacement?
Yeah, I think since our work, I think there have been two potential approaches. So there is the MoCo, indeed, where you can construct this kind of dictionary. And we haven't really tried to explore it yet in the multimodal domain. And another approach coming from DeepMind is this bootstrap your own latent, or BYOL. I don't know if you've heard about it. Yeah, as doing so. So yeah, again, we haven't tried in this video and text domain, but I believe those kind of are the right path to kind of free ourselves from this requirement.
Thank you.
Yeah. Cool. So yeah, if there are no more questions, I'll move on to the second part of my talk, which is about our NeurIPS paper from last December, which is called Self-Supervised Multi-Modal Versatile Networks. And this is a joint work with colleagues at DeepMind. And yes, I'll start with one video because so before, as I said, we haven't really explored using the audio modality. But as we are going to see on this example, this modality can bring something more.
Towards the root and try to get as close to the root as possible. Nice, long stroke.
Yes, so again, I'll play the audio once more.
Towards the root and try to get as close to the root as possible. Nice, long stroke.
So yeah, so I think it's fair to say that we learn from the world through a true multimodal experience. And in this example video, we have like both the visual signal of the chef cutting this onion. He also gives us some narration that we were previously using in the work I just presented. But as you may have here, there is also the audio track that contains additional information, such as the sound of the knife touching the cutting board. And this is something that we believe can be used to improve the representations further. And that's why in this work, we want to basically try to do self-supervised learning on kind of all modalities naturally present in videos, which are vision, audio, and language. And there will be like some questions that I hope I will give you an answer, which are three modalities better than two for downstream tasks and improving the visual representations? And also, like now that we have three modalities, what architectural designs are going to give benefits beyond performance? So I want to like give you some reflection and how one should like design the networks when being presented with like three modalities like this. And again, we are going to reuse the kind of the same idea that we have been leveraging in the previous work, which is to, for each modality, extract a representation. So for example, for the audio, we are going to get one vector using an audio network. Similarly, for the video, we are also going to extract like 3 seconds of video to extract a video clip. Similarly, for the language, we are going to extract a representation. And we're going to apply, again, a kind of multimodal contrastive learning approach, where we are going to have positive pairs coming from the same video and negative pairs coming from other videos. So for example, you have a video of the guitar. The sound of the guitar will be a positive for the video. The text, if the text is mentioned, will be a positive for the video. And we will sample other audio from other video, for example, this onion video, to get negative audio or negative text. Yes, and so basically that would be the main idea, and I'll move on to explain a bit more the details. So of course there has been some related work in the area that have been applied, for example, on the vision side alone with methods like SimCLR or CPC. Similarly, in the vision text domain, so the work that I presented earlier, also in the vision and audio domain. But we were kind of one of the first work to look at combining vision, text, and audio in this self-supervised domain. And one aspect that we have, and you may have found that like there is this versatile word in our title. And what we meant by that is that we wanted to have kind of a list of properties that our model should kind of respect to be called versatile. And we've like listed those four properties. So I'll first focus on the first three properties in the first part of the talk. So first, we want a model that can take as input any of the three modalities. Second, we wanted to respect the specificity of modalities, and I'll come back a bit to that a bit later. But basically, the idea is that not all modalities are equal. So for example, you can imagine that the audio or the visual signal is richer than the text that is a bit more coarse. So we want to explore if there are ways to have different ways to compare modalities that may have a different level of granularity. And finally, 3, we want to enable the different modalities to be easily compared. So as we were showing before, we wanted to have this score to be able to score a video and the text. And now we want to have a similar thing where we want to be able to score the relevance of a video and the audio, a video and the text, and the audio and the text. And the last property that I will focus on later is we also wanted our model to be efficiently applicable to any form of visual data, be it images or videos. But I'll come back to that later. So one first question that I touched a bit upon is when you have those 3 modalities, how to obtain the embeddings for each modalities. For example, before we had a single space because we had only 2 modalities for the video and the text. But now that we have 3, we can ask ourselves, should all modalities be embedded in the same space? Or should we instead have specific embedding space for different pairs of modalities? And we are going to explore these questions via network architecture options that we called embedding graph design. So the first option that may come to mind, and I guess it's maybe the most natural, is what we call like the shared space. So in that case, what you can do is basically take your audio modality, your video modality, and your text modality, and embed them in the same dimensional space, for example, of size 512. And all of them kind of live in the same space because you can compare the video and the text with the same representations that the one you use to compare to the video and the audio. So in a sense, that one is nice because it enables to compare the different modalities easily because they all live in the same space. So you can compare audio, video and text, and also audio and text. However, they kind of treat all modalities as if they were equal. But as I said before, maybe there are different levels of granularities, and you may not want to compare like the audio and the video in the same space where you compare the video and the text. So another alternative to address this issue is to allow for a specific treatment of modalities, and we call that disjoint spaces. So instead of having, for example, the same projection that will give you the representations for the video that will compare to the audio and the video that will compare to the text, you can use 2 different branches that will extract 2 different representations. So one to be able to compare to the audio and one to be able to compare to the text. So this is nice because now it allows for the specific treatment of modalities. However, it's now not easy to compare the different modalities together. And in particular, as I'll explain later, in our work, we do not train directly with audio text loss because the text directly comes from the audio via automatic speech recognition. So in that regime, it's not easy to compare the text and the audio after the network has been trained because you will kind of need to invert this mapping, which is not necessarily feasible. So yeah, it has this advantage of allowing the specific treatment, but it's not easy to compare the space because you cannot easily navigate across the spaces. So that's why we propose a third option, which is kind of a best of both worlds. And we call it the fine and coarse design. And the intuition here is that so the audio is more fine-grained. For example, there are multiple sounds of guitar, whereas text is more coarse. There is a single word for guitar. So that's why we propose this design where we have the audio space and the video space here. So we have this projection that projects into the audio text space. And then from that space, we take the video and we project it into the space where we are going to compare to the text space. So intuitively, this is this drawing here where we have one space for video and audio that we then project to the text space. So now we also have this property that it respects the specificity of modalities, because all pairs of modalities have a different space to be compared. But now it enables the different modalities to be easily compared, because even though, as I said earlier, we are not training directly with audio and text pairs, we can now compare audio and text later on, because we can take an audio representation. Since it lives in the same space as here, we can then project it to get a kind of vector where we can compare to text. So we can now navigate between all pairs of modalities. And also, as we will see later, this kind of design also gave us slightly better results in the downstream task, which was kind of encouraging. So again, here, this is our intuition about this fine and coarse, and we probably need to explore more along that space. But I think there is this idea of like the different modalities having different granularity, which might be interesting to explore further. So this is like the first kind of our first attempt to explore this. So I don't know if there are some questions here, because maybe this is a bit subtle. So I'm happy to answer questions about the architecture.
I just have a question regarding the loss. So you always do a pairwise loss in terms of contrastive learning, right?
Yes. So I'll have the exact loss afterwards, if that can help.
Okay.
So I can show. So yeah. So basically, just in terms of training data set, we are going to reuse the auto on-random data set, but we are also going to use the audio set data set that has a richer relation between the audio and the video, because it was collected for this. The only drawback is that there is no language, but our method can cope with missing modalities. And just to answer your question, in terms of the losses, yes, we only explore pairwise losses. And we explore in this work two losses. So one loss, which is the noise contrastive estimation between the video and the audio. So which will happen, for example, in that space for the fine and coarse design. And the MIL, so the multiple instance learning NCE for the video and the text. And basically, when there is no text in the video, we just do not have this loss, but audio is always present. And again, like we had made this kind of design decision that since the text was directly coming from the audio through ASR, we decided not to use a direct audio text loss. But as I will show later in the qualitative results, we are still able to learn a kind of semantic link between the audio and the text via the vision, which is kind of the common ground in this work. Does this answer your question?
Yes, thanks.
Cool. So yes, I'll first show some qualitative results because again, we, as a byproduct of this training, we are going to have this kind of joint multimodal space between audio, video, and language. So we can do retrieval. So for example, that's one example. So I'll play the sound. So if you hear, there is a sound of like people and the water, and those are the kind of the video that we retrieve that are closest to this audio. We can also look at sounds of like instruments. So it's kind of a sound of like a didgeridoo that is retrieved first, and the other nearest neighbors are also like kind of wind instruments. So what we can do is also still do text to video like we were doing before. So we can also input a text such as this one and retrieve the closest videos. And again, for example, in this case, at fresh chopped tomatoes and steer, we retrieve meaningful videos according to this query. We can do the same for other like text queries, such as like pour some oil into a hot pan. And again, we retrieve like correct videos. But another thing that is interesting is, again, so we had not trained directly with text to audio, but thanks to our design, we can do it. Basically, the idea is given a text input query, we can simply embed it into the joint space and retrieve the closest audio embedding. So you can take an audio, project it first into this video audio space that we had learned before, and use the projection that was only trained with video to project the audio embedding into the joint text, video, and audio embedding. And again, we can do some text to audio retrieval by doing so. And those are some qualitative examples to show that it seems that like qualitatively there is something happening. So for example, if we input the text airplane and we retrieve among some audio samples from the ESC50 dataset, this is the sound we retrieve. We can also like do another query. Yes, so as you can see, like those representations are nice from a qualitative perspective because you can really kind of use them to compare across modalities.
So one question regarding the results you showed before. So you search the whole database because the first direction is easy when you do text to latent encoding, but in order to get the closest sound, did you search the whole dataset, for example, to get the closest one?
Case, what we do is, so we take a dataset on which we have not trained on, which was ESC50. And the way we do it is, so I think in that case, in that experiment, maybe there were like a few thousand audio samples. What you do is like you extract all the audio embeddings from those your database, and you can just have a matrix basically. And now, given a text query, you can just do a matrix multiplication to get all the scores for all your audio samples directly in the database, and just retrieve the closest one.
Okay, yeah, I just wanted to know how you do it. Okay, thanks.
Yeah, cool, thanks. And yeah, in general, I think those like kind of embeddings are really nice because they can be scaled a lot because I don't know if you're familiar, but there are like some approximate nearest neighbor search algorithms where you can basically do this kind of retrieval into like million or billion scale databases. So yeah, there is an advantage of having those simple comparisons by dot product when you want to really do retrieval at scale. But so yeah, so those qualitative results are nice, but of course it's important to also evaluate the representation and their quality. So again, similarly to the previous talk, we are going to look at different downstream tasks. And we are going to explore how good is our video representation and also how good is the audio representation. And for that, on the video side, we use the HMDB51 and UCF101 that I introduced before. But we also explore a more challenging benchmark, which is the Kinetic 600, which is a larger data set with maybe more room for improvement. And in that case, because the data set is quite large, we only explore the linear setting where we freeze the representation and we just learn the linear on top. Yeah, I think there was a question before about like doing like 1%, 10% of the labels. So we are not doing that here, but kinetics will be a data set where such analysis would make sense. For the audio representation, we look at the ESC50 dataset, which is a small audio classification dataset, and the audio set, which is again a bigger dataset. So we've trained on this dataset audio set, but then we can train for classification and see how good is the representation. So first, some quick ablation. So yes, so this is the embedding graph design ablation where we compare the shared, the disjoint, and the fine and coarse design. So overall, we observed that on the video benchmark, the fine and coarse design was performing a bit better than the alternatives. And overall, on the other, like audio and text to video, it was also performing quite good. And in particular, we observed that it was kind of always kind of competitive with the disjoint approach, which was like having those, modeling those modalities in a specific manner. But this fine and coarse design has this additional advantage of being able to compare all modalities. So we basically kind of reached the goal of having something that has the best of both worlds. Another important question that we had in the paper was like, do more modalities help? And we observed in this ablation on the UCF and HMDB linear that it was indeed the case that, so that was trained only on the output data, where we observed that learning from video, audio, and text does improve over only training from video and text or only from video and audio in both benchmarks. So that's also like kind of in line with like our intuition from the beginning. Finally, like, so yeah, self-supervised learning from video is becoming kind of yeah, a kind of competitive area. And at the time, and I think it's still the case, we were state of the art on the two standard benchmarks, which are UCF 101 fine tuning. So where we obtained like 95.2 top one accuracy. And that was to compare to the 91.3 we were obtaining with the previous work I presented. So like a large improvement on this benchmark. And then on the HMDB 51, we got even a bigger improvement compared to previous work, and especially compared to our work. So there, the audio additional supervision seems to have bring a lot of benefit. We also show on the EST50, which is an audio classification dataset that we obtain. I mean, close to state-of-the-art performance. So there is a AVID method that was performing slightly better. But those are really good performance on this benchmark. And finally, something we explored in this paper is that those datasets that I presented, UCF, HMDB, and EST50, are rather small, and they start to saturate a bit as a benchmark for self-supervised. So we also propose and explore two larger scale benchmarks to evaluate self-supervised representation. And we propose the linear evaluation on Kinetic 600 and the linear evaluation on audio set. So since this benchmark is not yet used, at the time we made a good improvement over previous methods. So we got like 70.5 top one accuracy versus the previous best published self-supervised, which was only doing 64. And on the audio set, we were getting 30.9 MAP, which was better than the previous self-supervised model at the time. And now, like, there are more work that are, for example, using the linear evaluation on kinetics as a downstream task. Yes, so if there are some questions about this part, before I jump to the part about how to transfer video to representation to images, I'm happy to answer them.
Can I ask a question?
Yeah, sure.
So regarding the results you showed about the comparison of modalities, if I remember correctly, you said that you get the text from the audio, right? Previously in your data?
Yes. So I get the text from the audio, but when you do that, so you simplify a bit the representation, because now the speech is represented in a form that might be easier to learn from, because it kind of removes all the kind of the tone of the people or things like this. So that's good, but however, you lose all the ambient sounds, for example. So you remember in my example, the sound of the knife that was cutting on the cutting board. That one was lost. So that's why I think we can extract better representations by leveraging the audio. And finally, another answer is that, so in this ablation, we are not using audio set, but when you add on top audio set, which, for example, does not have necessarily the language, but only has audio, then like you get even better improvements. So yeah.
But the fact that basically the VA is worse than VT, that means that probably there is still difficulty in extracting the information that is already there, right? Because you should have all the information in the audio.
Yes, yes. But I think it's quite challenging to get the semantic of the speech, especially with the kind of model we consider. So the model that we consider on the audio side is just a CNN applied on the applied on the log spectrogram of the audio waveform. And I think it's pretty hard to do speech recognition with such model. So it's really hard to extract the semantic of the word from such models.
Yeah, that's probably the reason. Okay, makes sense. Thanks.
Sorry, sound. Yes, cool. So yeah, maybe I'm starting to be a bit out of time, so I'll try to just explain the last bit, if it's okay. So yeah, the last thing we wanted to have is to be able to efficiently apply our kind of representation, not only to videos, but also to images. And so for that, we introduced what we call network deflation. And this is our motivation was like, as a human, we usually learn from continuous stream of data, which are roughly approximated by videos. However, most work usually try to first learn representation on images and then transfer them to video. So for example, in a famous work from the i3D paper that first introduced some like 3D network for video, they start from a model trained on ImageNet and they inflate it. So they inflate the 2D filters into 3D filters to be able to be applied to videos. So instead, in this work, we wanted to do the opposite, meaning we want to learn from video and then transfer to images. And what we wanted to do exactly is to have like, yeah, our model, we wanted them to be applicable off the shelf on images without any adaptation. And we wanted that adaptation to be efficient when applied to images, because when we have a video, we have like multiple frames, but when you have one image, you don't want to like have the same cost as running on the full clip. And basically, a standard approach for that is to do what is called inflated input, where you take an image and you repeat it, like, for example, 32 times to emulate a kind of a video where nothing will be moving. But instead, what we propose is a deflated network where instead of repeating the input, we kind of compress the video network into a 2D network, so from a 3D network to a 2D network. And now we can input a single frame. So basically, we are much more efficient by doing so. And the approach that we use is basically we can deflate the 3D convolutional kernel into 2D by just summing along the temporal dimension. But what we observe is that this was not directly working out of the box because there is a temporal padding effect that on the border of the video usually pad with zeros for the convolutions. And we observed that we could retrain just the batch norm parameters, the gamma and beta, in a self-supervised way to just match the output of the input inflated network with the output of the deflated network. So we have a simple loss that basically adapts a bit the weights of the network to kind of counter the effect of this padding. So then what we do is we take this network and we evaluate it on two image benchmarks, which are Pascal and ImageNet. And so we show different things. So first, we look at what happens if we take a network that was pre-trained on kinetics, which is the kind of the standard for action recognition. So it's trained in a supervised way. And we evaluate it by inflating the input, so the kind of the slow technique, but that works well. That usually works well. Then we take our network, the MMV fine and coarse that we train on auto and audio set, and we do the naive deflation that I've talked about before, where we only deflate the filter, but we don't do this extra adaptation to counter the effect of padding. So that performs quite poorly compared to when we do the input inflation technique, where we repeat the frame, but again, a technique which is not efficient. And then when we propose our deflation technique, we can recover the same kind of performance that we have when we inflate the input, but now we have a much more efficient network that can run much faster on images. So this is the kind of the performance we get. So compared to pre-training on kinetics, we have a large improvement. But of course, we are still a bit far from what you can obtain with SimClear trained on ImageNet directly. So one challenge that remains will be to kind of close the gap between pre-training on ImageNet by just using videos. And you can see that on ImageNet specifically, we are quite far from the performance of SimCLR. So I'll just give some key takeaways, and I can take some questions. So basically, we kind of propose a general framework to learn representations by aligning different modalities. By doing so, we achieved state-of-the-art results for self-supervised learning in several downstream tasks. And I think we propose one step towards transferring from video to images that I believe can be quite important in the future. Something that we've only explored qualitatively, but might be interesting to explore quantitatively is new applications such as zero-shot text-to-audio retrieval or text-to-audio classification. So yeah, I'm happy to take some questions at this stage if we still have the time.